The last PowerPoint of this graphs unit is called Optimization of Graphs. It's very lengthy, there's lots going on, but we'll get through it. The first thing we're going to talk about is the path of minimum value. Then we're going to talk about a tree of minimum or maximum values, the chromatic number of a graph, and critical paths. First, the path of minimum value. In a weighted graph, you can determine the path of minimum value by adding all the weights in a graph. When you're connecting two vertices in a graph, mark down the path of a minimum value. In the graph below, the initial vertex is A and the final vertex is F. Here it is, and you can see that every edge has a weight. At each vertex, you should write the path of minimum value. So from A to B, the path of minimum value here is just, there's only one choice, so it's worth 4. From A, B, and C, the path of minimum value is 5. Notice that you can get from A to C by crossing through D, but then you'd have a higher value. 9 plus 3 is 12. So the path of minimum value from A to C is A, B, C. Over here, we have A, B, C, and D. Note that the reason why we chose A, B, C, and D is because the minimum value here is 8. Since if we go from A to D, it's 9, which is more than 8. So the path of minimum value to this vertice, or to this vertex, from the starting vertex is A, B, C, D. For here we have A, B, C, E is the path of minimum value from A to E because it's worth 9. And finally, to get from A to F, the path of minimum value is to go from A, B, C, E, F, which is 11. Note, though, that we also just calculated all of the weights of the edges that we took from getting to A to F. The tree of minimum or maximum value. When given a graph, you may be asked to determine its tree of minimum or maximum values. You need to remember that a tree is a graph that contains no simple circuit. A tree also includes all the vertices of the original graph. The following are steps to finding a graph's tree of minimum or maximum values. Before we go on, I'm going to tell you what it is to do the minimum, and in brackets, it's what you need to do to find the maximum value. Find the tree of minimum or maximum values for the following graph. First step is to select the edge with the lowest or highest value. So remember, lowest meaning minimum, and whatever is in the brackets is what you need to do for a maximum. But I'm going to stick with the minimum. So you select the edge with the lowest value. In my case, it's FC, which is 5. Step 2, of the remaining edges, select the one with the lowest or highest value. So I'm doing minimum, so I'm going to do the lowest. So out of all of these edges that you see here above, the second lowest value after 5 is 6. So I'm just going to draw it again. Repeat step 2, meaning finding the lowest and again the lowest and again the lowest of the edges that are remaining, until all the vertices are connected without obtaining a simple circuit. So the lowest one that I had was FC, which was 5. Then I had ED, which was 6. The next one that was low was 7. The one after that is 9. And I need to connect all of my vertices, so the one after that is 10. So now I have a tree of minimum values. All my vertices are connected, and it's basically all the minimum values of a graph, and that's how you do it. In my case, I did it with minimum. You can do the same thing, but instead of doing lowest values, you do highest values. The chromatic number of a graph. The minimum number of colors necessary to color all of the graph's vertices without any two adjacent, and remember, adjacent means just vertices that are side by side, without any two adjacent vertices being the same color. Here's how to do this. You must determine the chromatic number of the following graph. Remember, I just want to know how many colors can make up this graph. So this is how you do it. Here is my graph. First step is to color the vertex of the highest degree. In this graph, A is the vertex with the highest degree of 3, so I'm going to give it one color. Color the vertices adjacent to the vertex of highest degree with another color. Remember, don't give two side-by-side vertices the same color. So over here, my highest vertex is A. If you can identify the adjacent ones right away, you will see that B is connected to A, C is also connected to A, and D is also connected to A. So these three, B, C, D, are adjacent. So because they are adjacent, we have to give them another color. So I'm going to give B and D green, and I'm going to give C purple. Why can't I give C green? Because if I give C green, then B and C, which are adjacent, will have the same color, and we don't want that. Finally, color the other vertices with colors that have already been used if possible, and if not, use another color. My only remaining edge here is E. So it's attached to D. I have a choice then of either coloring it orange or purple because I need to use another color that's been used. I definitely can't use green because green is the one that's adjacent. So instead I just used purple. In conclusion, the number of colors that we use in this graph to color our vertices is 3. We have orange, green, and purple. So the chromatic number of this graph is 3. Try to find the chromatic number of this graph. If you begin with the vertex of the highest degree, you're at A again. Then the adjacent vertices you would have to determine are B, C, D, E, and F. Choosing the color blue, I decided to color B, C, E, and F blue. But I couldn't color D blue because it would be the same color as one of its connecting vertices. So I decided to change it to green. My remaining vertex was G, and I could choose to either make it purple or green, but I definitely couldn't make it blue because if not, two side-by-side vertices would have the same color. So I chose to make it green. Therefore, the chromatic number of this graph is 3 because I have 3 colors for my vertices. Critical paths. Critical paths are used to determine the minimum amount of time required to carry out a task comprising of several steps. I'm sure in your life you've had to do a task or a chore that required you to do it in either several steps or one step. Regardless, you have time and you have things that you need to do sometimes before the task. So you make a list of things that you have to do. In life, sometimes these tasks are easier to carry out if you make a critical path. This is how you use paths and graphs in real life situations. Here's an example for a need of a critical path. You want to start a company. So if you want to start a company, there's a few things that you need to do. Here are some steps that you must take before you start your company. Here, the steps are labeled with letters. Each step has a title, and it has a certain number of days that I'm expected to take to complete that step. And over here, I have listed out what steps do I need to do before I do that step. Beginning with A, I have to prepare a business plan. I don't have to have any prior steps, but I know that it's going to take me 30 days to complete. I have conducting market research, looking for partners, and looking for a location. So this is my BCD step. I tell you how many days it'll take to complete each of these, but I also tell you that the only way for me to complete B, C, or D is to have A done. So I can't do these 3 steps before I do A. For step E, I need to analyze the market research, and the only thing that I need to absolutely have done before getting to E is B. This takes me 5 days. For F, to evaluate the product distribution system, I absolutely need to do C and D before I do F. So in this case, these are my prerequisites, and it takes me 15 days to do F. For G, I have to arrange for financing. The steps that I need before this are E and F. I need to analyze the market research. I need to evaluate the product distribution system before I arrange the financing. So I need E and F before this, and this will take me a total of 35 days to do. And finally, my last step, H, is launching the company. This takes no days, but I definitely need to do step D before I do H. Knowing all of this, you can create a graph. And because we have execution times or days needed to complete, this will be a weighted graph. So the steps in this table can be represented using a graph where each vertex that we have in the graph corresponds to a step. We have A, B, C, D, E, F, G, H. Parallel paths are associated with steps that can be executed simultaneously, meaning if you see a parallel path in a critical path kind of graph, that means that those two things can be done at the same time. The number at each arc corresponds to the execution time of the step at the arc's starting point. Because this business plan or because this starting a company plan has steps that are needed before other steps can be completed, this graph will have both weight and direction. Let's begin with A. We can't do B, C, and D before we do A. So A will be our first vertex. Coming out of A, we're going to have 3 directional arcs going to B, C, and D, remembering that step A will take us 30 days. So we get to B, 30 days have gone by. We get to C, 30 days have gone by. We get to D, 30 days have also gone by. At B, we're going to connect this to E because E needs B to be done. Not forgetting that B needs 10 days to be completed. Coming out of C, which takes 25 days to complete, we're going to have F because we can't do F before doing C and D. So when we get to F, we definitely need to have C and D connected to it because we can't do F before we do those 2 steps. Not forgetting that it takes 20 days to complete D. So when we get to F, C has been completed in 25 days and D has been completed in 20. Going from E, we're going to get to point G because point G needs E and F to be completed. E will take 5 days, so before we get to G, 5 days have gone by for E. And from F to G, F takes 15 days, so we have here from F to G 15 days. And last but not least, we have one more path here from G to H, officially launching your company. But before we can launch our company, the prerequisite step is G here. And G takes us 35 days to do. And this is how you build a critical path. Now that we see our critical path, we can see that there are 3 paths to get from A to H. The first path you could see is A, B, E, G, and H. Our second path is A, C, F, G, and H. And our final path is A, D, F, G, and H. The critical path is the one which requires the minimum amount of time. If we calculate, we can label each vertex with a path of minimum value. The path of minimum value here is 30, here is 30, and here is 30. Here is 40, here is 50, here is 70, and finally you would be able to determine that the path of minimum value from A to F is ACFGH and its weight is 105. Since it is the shortest path, it would take a minimum of 105 days to start the company. Just a small warning. It is said that a critical path corresponds to a simple path of maximum value. But in many cases, the maximum or best value for something is to find its minimum. Meaning, in our last example, the maximum value, the best value, is actually the minimum amount of time it would take for you to start your company. If it takes you more than 200 days to make your company, you're not maxing your value. You're taking too much time. So you want to maximize your value by actually getting the minimum amount of time. Let's recap this PowerPoint. We started with the path of minimum value. In a weighted graph, you need to pick the path that has the smallest weight. Usually we write the smallest path or the path of minimum value at the top of each vertex in brackets with the weight after a comma. Then we talked about the tree of min or max value. Remember that trees mean that there are no simple circuits. The steps to do this were to select the edge with the lowest or highest value, select the edge with the next lowest highest value, and then repeat step 2 until all the vertices are connected. The chromatic number is the minimum number of colors necessary to color all the graph's vertices without any two adjacent vertices being the same color. And remember, adjacent vertices just means vertices that are side by side. The first step is to color the vertex of the highest degree. The second step is to then color the adjacent vertices or the vertices beside that highest degree with another color. You need to make sure that no adjacent vertices have the same colors. Step 3, color all the other vertices with colors that have already been used if possible, and if not, use another color. Finally, we looked at a critical path. It's needed when we want to find the maximum value of some kind of project, plan, or path. The time it takes to finish a step of your plan is the weight of the path. Some steps can't be done before another step, and we call those prerequisites. When you've completed your graph for the associated question, you need to find the critical path by mapping out each path and calculating its total weight, which we did a few slides ago. Usually the critical path is the path that is the best for the situation, and sometimes that can be the path with the lowest weight. So be careful and make sure you understand your question. That is the end of section 3.4, and that is the end of chapter 3 on graphs.